Welcome everyone to the Black Hole. This is a community space, recently started, and some of you have been here before, some have not, so let me say that this is intended as a place for open, free discussion on practically anything under the sun. We have had a long list of events, something like one a day, maybe some often twice a day. Today's event is with Dr. Saleem H. He is a distinguished professor at the University of Delaware in the Department of Geography. He received his PhD from MIT in 2000, which is 22 years ago. And the interesting thing is that I preceded you by 22 years exactly. It's 1978. Before that, he was at Yale University, and before that at Tufts University. So he's experienced the educational systems of the United States. He's also worked on a large variety of topics, of issues that deal with mining, resource extraction, their impact upon the natural environment, upon society as well. And he today is here because he's to launch his book, Earthly Order. Now, when you look at this, you say, Earthly Order, what does that mean? Actually, it's order about everything from the earth to the heavens, because within this is an amplification of principles that govern the natural world and also the world of living beings, of humans, of human society, of economics, of politics, how this is all organized and how order emerges out of chaos, how we can perceive patterns and simplicity in what appears to be overwhelming complexity. That is really the book, but I will stop here so that Saleem can tell you what this book is about and whether in fact I have understood what it is. So I think the way we should proceed on this is that perhaps you could tell us a little bit about the book, and then the questions that come to my mind I will ask of you. We have started a few minutes ago. We shall go on for maybe another 55 minutes from now, after which we shall have an open discussion with the audience, and you will be free to ask whatever you want. So, Saleem, over to you. What is this book about?
Okay. Yes, well, thank you so much, Professor Hudba. It's a real pleasure and honor to meet you for the first time, though we've had exchanges on email, and it's great to be at the Black Hole. I hope that it continues to be a source of gravitational attraction for intellects across the country. I'm somewhat humbled by this effort, because the origins of this book actually come back to Pakistan, and I in fact mentioned that in the book, that this is a book that is written from both a personal perspective and also from the point of view of promoting environmental literacy, what I call environmental literacy rather than environmental awareness. I think we all have a lot of environmental awareness, but we don't have environmental literacy. And it goes back to that sense of, as a child, I grew up in Lahore, even though I was born in the US, but I grew up in Pakistan. And I was often having to confront this sense of how does this country seem to, function with all of the other challenges that it has and so on. So there's a sense of chaos, and then somehow we are constantly trying to also find a way to chart a path towards order. So it has its origins in that sense. But you know, you then try to go back to the natural sciences. My first degree was in chemistry, and I wanted to try and understand, is there something foundational? Is there something fundamental around the laws of nature which can give us insights into how social and political order also function? And that's what makes this book quite daunting to write, and to do it also in a way where you're not contrived in terms of how you present the information. Because the thing with patterns is that patterns are very seductive. When you see a pattern, you feel as though there is something there that may itself be an illusion. And so patterns can lead us down paths which are not always true. And that's why we often get some of the tensions between issues like science and religion or other kinds of factors, because patterns themselves and a sense of order can lead us in that direction. So that's kind of the root of the book. You know, it's like it came out of my childhood in Pakistan. In fact, I can even start off with just a few sentences to give you some context in that regard of where this idea came from. So I'll just read a few lines from the introduction. Shattered pieces of glass fragments funneled into a metal tube with angled mirrors and a peep-holed cap give you a remarkable little invention. Do you know what invention would that be? Anyone know? Yes? Fiber optics. That's a true sign. No, it could be a kaleidoscope. Yes, no, that's true. But I'm glad when fiber optics are made of glass as well, so that's fine. The Scottish inventor, Sir David Brewster, patented this little science toy and called it a kaleidoscope. The name stemmed from the ancient Greek word kalos, meaning beautiful, and eidos, meaning a shape which is seen. The random shapes of the glass, when confronted with the regularity of light reflecting infinitely between the angled mirrors, creates order to the beholder. Order can thus be defined as the manifestation of patterns that can be perceived as differentiators by the observer. Structures such as rules or laws, we have a lawyer here as well, are needed to maintain such order. Patterns emerge from every shaking movement of the object. Each one is different and yet predictably fascinating. What captivates the observer is the seamless transition from the seemingly chaotic act of shaking to the viewing joy of structure. Brewster's simple invention tapped into a human yearning for being surprised by order. Within 3 months of his commercial release of the kaleidoscope, in 1817, more than 200,000 were sold in Paris and London. As a child growing up in Pakistan, and that's why I wanted to do this part here. I mean, other book launches, I wouldn't talk like this, but this is because of the Pakistan connection, I wanted to bring this up. As a child growing up in Pakistan, the kaleidoscope was my favorite toy. You could buy a variety of paper-tubed ones, which local street toy makers would make from cheap Chinese mirrors and some broken glass bangles or pebbles. Light beamed through the translucent end of the tube to illuminate a colorful pattern of the glass fragments. This happened simply because of the structure imposed on these random objects by 3 glass mirrors. Beams of light could functionally enchant an inanimate world. The velocity of light is considered the upper speed limit of the cosmos. I imagined the light passing through the glass, shifting and scattering as its speed was reduced ever so slightly. Still further, I studied the chemistry of water and saw the formation of snow crystals, analogously to my beloved kaleidoscope. Each flake is unique insofar that its creation captured the moment of a dust particle that was encircled by cold water molecules in a crystal structure, in a crystal embrace. Yet all snowflakes also have a predictable 6-fold symmetry due to the fundamental nature of how water molecules arrange themselves in crystalline form. What one may call ordered diversity in natural phenomena has been a lifelong fascination for me. So each snowflake crystal has this predictable aspect to it, but each is unique. So this aspect of nature is something that then translates into social and political order as well. Attending an all-male school in Pakistan, that was Aitchison College, I experienced how strict social order was considered an essential prerequisite for success. There were clearly defined views of natural order that were linked to social order, perceptions of how gender roles were to be defined with ostensible predication on the natural properties of each gender. There were notions of how lives should be ordered around particular milestones of college, marriage, children, caring for elderly parents, and then memorializing their passing through prayer. As I grew older and was exposed to a broader range of learning, my views of order changed, and I reveled in somewhat rebellious anarchy. Yet the need for some modicum of order to manage resources on our planet, and indeed our own personal lives, remained ever present. Writing this book is a quest to find key insights from the coexistence and interplay between functional order and disorder, and to link it to the quest for sustainability in human interactions with our planet. So that kind of gives you a sense for the motivation of the book. But in terms of the book itself, it's very, I would say, simply structured in terms of three parts. There's natural order, social and economic order, and political order. And the ultimate goal is, that's why it's called earthly order, and because I'm an environmental planner, is how can we use our notions of order to chart a course towards sustainability. I don't want to just pontificate about, well, this is complex system theory and this is this theory or that theory. I want to use it in a way where it can be actually helpful in charting a course towards sustainability. So one example I will give you, which is relevant to the news recently. If you go to your field, physics, we are constantly trying to figure out the sort of the material energy nexus, right? How are we going to be able to have energy flows that are functionally useful to drive human activity? And for that, we need some foundational knowledge of physics, whether we want to derive nuclear energy, in terms of nuclear power. The concept of energy density is a very powerful one, but it is completely missed by many people in our energy planning and policy fields, right? So if you look at what has happened in Europe last week, the European Parliament had to pass an emergency legislation. Does anyone know what the emergency legislation was on? It had to do with energy. The Europeans before, a few years earlier, had decided that they were going to phase out nuclear power, especially Germany said that they were going to phase out nuclear power. And they called it a legislation system around taxonomy. It's actually called taxonomy, the taxonomy of energy. And they had classified nuclear energy was not a clean energy. It was classified as dirty energy, and so certain funds which were to go for development of nuclear energy could not go there. Now, because of the Russian invasion of Ukraine, the cutting off of gas supplies to Europe put Germany particularly in a crisis situation. So in order for them to then recraft their whole policy, they had to list nuclear energy back as clean energy. And they passed an emergency law which made natural gas and nuclear both clean energies, because their policy formulation had been completely divorced from the basic understanding of energy density and the fact that when we deliver electricity, we need to have baseload power, and then you can have fluctuations for wind and solar and so on, right? What are the different ways in which you can have baseload power? Currently, we have only three ways to have baseload power. It's either oil or gas or nuclear. Those are standard. Now, gas can be biogas. It doesn't have to be natural gas coming from fossil fuels, but that's the only ones we have currently. Solar and wind, if you want to have them as baseload power, what do you need? Again, basic physics, which you would need from the point of view of being able to have constant delivery. You need massive battery storage, right? If you had massive battery storage, then you could deliver baseload power from it. Now, the energy planners in Europe never thought about all that. First of all, they don't have the battery storage capacity. Secondly, for baseload power, they were assuming that they would just be able to transition from fossil fuels slowly towards this. And so they did not consider this concept of energy density and the importance of baseload power. And so you had an errant policy decision, which they had to correct. So those are the kinds of things which happen when you do not have natural order, understanding of natural order in sync with political order. In many cases, similarly with social and economic order. So that's just one concrete example, but there are many others as well in the book which go through that.
Well, certainly we can get into the policy domain, but after a little while. Because
Sure.
when you say Germany said no to nuclear power, there was a very definite reason for that, because there was a great deal of fear, and there remains that fear of what would happen in the case of a nuclear accident. As happened in Chernobyl, as happened later in Japan with the Fukushima disaster. So we'll get into the policy issues in a bit.
Yeah.
But let's go chapter by chapter through your book. That might be a little more systematic. So if I could have the book.
Yeah, would you like
to? At least the chapter titles will be useful for us to look at. Okay, so you talk about the seduction of structure in nature. That's chapter 1. Seduction of structure in nature. Nature seems to us to have order in it, patterns in it, a fundamental. There seem to be laws, laws that can be discovered by the human mind and used to interpret what is around us. And so let's take just a couple of examples to establish that. The periodic table of the elements, discovered by Mendeleev, beautiful illustration of that. We have 100+ elements with hugely different chemical properties. And yet we can understand that in terms of simply the orbital motions of electrons, just electrons. So you have electrons, if they are 2 in a shell or 8 in a shell, 18, whatever, and then subshells. As we improve our understanding, we know that you don't need exactly 8. You can have 10 sometimes, but then there'll be energy differences over there. In that way, we understood the entire chemistry of all that there is on Earth. To give another example, once upon a time, it used to be thought that they were just neutrons, protons, electrons, and of course, photons. And then, as we started colliding particles together, we found new particles being created. And at first, there was a lot of excitement. Oh, there is the K meson, there's the rho meson, there's the omega meson, there's the lambda baryon, there's this, there's that. And then it became very embarrassing. Very, very embarrassing, because the number of elementary particles started to go up and up and up. And these were particles that were not found in atoms. So how do you explain them? And that's where the idea of quark came about. And those quarks were organized in very particular ways. So there's something called the eightfold way, remarkably, and it's something that can only be understood by the exercise of mathematics. Mathematics gave us the idea of what is called a group. That group had as its basic representations the quarks. And so a vast variety of new particles could then be understood as such. Okay, so the examples after examples on this, I won't take any more time on this. We have laws which are simple. So I could write down, the laws which govern the behavior of quarks in this much space, or on this board as much as life takes over there. And you can understand, in principle, everything about quarks from that. There are no such laws for society, no such equations. So let's start from that. What do you
Yes,
say?
so this is the fascinating part around translating from what are foundational laws at the level of quarks and particle physics and moving on. So one of the people who is credited, of course, with the discovery of quarks, Murray Gell-Mann, the Nobel laureate, he wrote a book called The Quark and the Jaguar. And he's considered the founder of the field of complex systems theory, which is partly what this book is. The underpinnings of this book are around complex systems, which is that you can have emergence of complexity from very simple kinds of interactions, and you can have emergence. That's how life emerged. The emergence of life is a complex systems phenomenon. From very simple interactions, you can get that kind of dynamic. And so you're absolutely right that in many ways, you have to be careful as to what level of that translatability you can have. But there are some structural aspects which are absolutely translatable. Like, for example, the way in which a stampede happens, in a certain context, is very similar to, if you go back into complex systems, it's the way in which particles would behave as well in a certain way under certain conditions. The ways in which cities emerge. One of the other physicists who worked at the Santa Fe Institute, Jeffrey West, who was the president of the Santa Fe Institute, he wrote a book called Scale. And scale goes into this notion of power laws. That power laws, the same power laws which you apply at particle levels, you see them at the way cities grow. Cities grow in the same way in which you would have those kind of growth patterns. So you can have that, but you have to be careful that where human agency is involved, order is not just discovered, but it can be invented. And that's I have 5 lessons at the end of the book, and one of those lessons is order can be discovered and invented. And so you cannot have an equation in the same way for the way in which social functioning is going to happen. That's why economists have trouble. They try to put equations and their models end up often having to be corrected because they are not able to be. They can approximate what happens, but human agency can make those things happen in a different way. So you're absolutely right that you cannot have the same level. And there's a graph in the book, actually, in chapter 4. It is from John Barrow's work, in which he talks about whether you can have an equation for something and whether you have what's the level of predictability. And he puts all these different domains of knowledge on it. And sociology is at one extreme where you cannot have an equation about it because it's not predictable in that sense.
Yes, since this is a little off the topic, but since you mentioned Jeffrey West, he's a physicist at Los Alamos, and met him a few times. He has a very interesting book on scales.
Yes, yeah.
And one of the interesting questions he asks is, which is stronger, a mouse or an elephant? The answer is, of course, a mouse. A mouse can carry much more weight. No, he asked, which is stronger, an ant or an elephant? The ant, Chunti, is much stronger than the elephant because it has to have much thicker bones or whatever those things are as compared to that of an elephant. And he does this on the basis of looking at how wide a load-bearing column has to be to sustain a certain load. And you can ask, which eats more, a mouse or an elephant? And the answer is a mouse. Anyone want to know why? Well, because we're all mammals and we all have the same surface temperature. So yours would be 98.4 degrees Fahrenheit if you're not sick right now.
Beats faster, they control body heat.
Huh?
Its heart beats faster rather than the elephant.
Okay, that's another interesting point.
Yes.
But you see, you're sort of right. Yeah. No. Please let him speak. We're all happy that he speaks.
Younger generation.
Look, if you have an ant, think of an ant as a little cube, and think of an elephant as a big cube. What is the area of a cube? 6 times the area of one face, right? What is the volume of a cube? It's the length times length times length. Take that ratio and it's 1 over 1 length, a length. And so, because you dissipate a lot more heat, and that depends upon the surface area, it's very easy to show. I could show it in 2 minutes. Why a mouse has to eat so much more in order to maintain its surface temperature. But anyway, that's so. This is a sort of scale.
Exactly, the power laws.
Yeah. But the question that came to my mind was, equations can be very simple, and yet what they can lead to is something very complex when those equations have chaotic solutions in them. So perhaps you can tell us a little bit about chaos, how it enters into looking at the analysis of problems.
Yes, so chaos and order are this kind of yin-yang that we constantly deal with in the universe. And one really interesting example, which goes back to how some of the origins of chaos theory development go back to our alma mater, MIT, where there was a guy named Edward Lorenz. And Lorenz was interested in atmospheric phenomena. So he was interested in wind patterns and all. And what he found was that you get these kinds of wind patterns emerging in ways which are not predictable at the short scale, but they could be predictable at the long scale. So this is the paradox that we are talking about climate change. We are able to predict to some degree how much climate change may happen over the next 10 to 20 years, but the most we can predict with weather is up to 10 days, right? You won't find any weather forecasters. And the reason for that is this yin-yang chaos order problem. Because at the short scale, at the granularity level, you just get so much chaotic distribution of weather patterns and so many variables interacting that you cannot find a way to predict accurately. But if you look at the long term and you find those patterns coalescing, they will move towards some kind of convergence, which will lead us to predictability in climate. So Lorenz was one of the founders of that approach of, and last year's Physics Nobel Prize was actually given for people who did climate modeling, because it goes back to fundamental physics. Lorenz died, otherwise he would probably have won it as well. But so that's an example of how you can apply this chaos order dynamic in an almost a paradoxical way to understand this relationship.
Yes, in fact, it's a property of some differential equations, second order differential equations, that a small change in the initial condition can lead to a huge change in the final result, provided that that is long enough. And so there's that whole issue over there. You could certainly have many other examples, but perhaps you want to talk about fractals and how they occur in nature, because you've mentioned them over here as well.
Yes, so fractals
That's related to chaos.
Yes, absolutely, yes. So there was a mathematician by the name of Benoit Mandelbrot, whom I had the pleasure of meeting before he died, actually. He was the guy who started fractal theory. But basically, it's like, if you think about any kind of a tree of life or a tree of anything, you are getting these different kinds of nodes emerging from one node and then bifurcating into different paths. And so fractal mathematics is a way to understand that kind of emergence, of how from one point you are able to get to all these others. But and he actually came up with this, some of his students did, and there's a diagram in there of what is this pattern of what you can get from fractals within the confines of sort of the laws of nature, and it's called the Mandelbrot set, and it looks like it's a beautiful diagram you can show in there, but it's sometimes people call it the, just colloquially journalists call it the thumbprint of God, because all of these different natural laws seem to converge on this kind of a pattern system of the fractals coming together. Yeah.
So these are very interesting conceptual advances, and I think one of the many interesting things about fractals is how long is the coastline? How long
Yes.
is the... If you look at, let's say, the coast of Britain, it's a little island, they ruled us for a long time. But suppose you were to measure all around Britain, what length would you get? 1,000 miles, 1,500, I don't know, something like that. But it would depend upon how you would measure it. Mm-hmm. Suppose you were to look at it microscopically and you were to then twist in and out as you increased your resolution further and further, you would have to move so much in such a complicated way that if you had this micro measuring stick, what you would measure by adding up all those distances would not be 1,500 miles, it would be infinity.
Yeah. It depends on the granularity.
Exactly. It depends upon the granularity
of what you want to do.
Exactly, exactly. So the great lesson that comes out of fractals is that what you look at depends upon the scale at which you look at. And to give another example, you look at the sky. It is more or less uniform. If you look with a powerful enough telescope, the number of stars that you would see and galaxies that you would see in, let's say, this much opening of a telescope will appear to be almost the same no matter where you look. But as you increase the resolution, you will find 1 part in a million difference between here and there. And that's the large-scale structure of the universe, and very, very revealing.
Indeed.
So all that is the natural world. Now, we look at the world of economics. What do you say about the applicability of laws deduced from the natural world applied to economic systems? How successful has it been in your opinion?
Well, I think in some areas you can see that economics has actually decoupled from natural laws, which is why we have so many problems in terms of economic systems, because there has been this sense that you can have, especially in neoclassical economics, you have a sense that the market will be able to somehow find emergent qualities which will be in an equilibrium that is sustainable, right? So economists have given so much credit to the market that the market will emerge in a way that will be sustainable. But if markets are confined by landscapes, or what we call, even in evolutionary biology, you call evolutionary landscapes, where they are not going to emerge in a certain way that's going to be sustainable from a physical point of view, then you run into trouble. That's where you get into situations where you have runaway growth that is leading to unsustainable outcomes. There were economists in the early days who tried to say that we need to apply, for example, entropy law to economics. There was a wonderful Romanian economist, Nicolas Georgescu-Roegen, who wrote a book in the 1970s called The Entropy Law and Economics. He was a professor at University of Maryland for a while and other places. He was not taken very seriously, even though his book was published by Harvard University Press. It was, peer-reviewed, really well aligned. But there was a sense that he was being too much a naturalist. He was being too much, determined by what the natural laws are. And so what has happened with economics, and I talk about that in section 2 of the book, is that economics unfortunately did not keep up with that sense of congruence, even though there were some visionary economists who wanted to. Now there is a whole new field of economics, which we call ecological economics, that has attempted to bring that back, where we are trying to align some of those design of market systems, which are more in sync with the natural systems and the constraints of natural systems.
Do you think there has been an over mathematization of economics?
Yes, yeah. I think so.
Because look, mathematics is a lovely subject, but it should be applied where it's relevant. If you apply it where it doesn't really apply, where the assumptions are not really true, then you can get into serious trouble. The examples of failure are so many before us. There was the great crash of the stock market in 2008. Nobody saw that coming. None of the greatest economists in the world saw it approaching. And then, as you jump off the cliff, everything disappeared. Well, you could say a lovely example of catastrophe theory. By the way, do you know catastrophe theory used to be so popular? It used to be the rage among mathematicians about, I think, 15, 20 years ago. I looked at it, I said, okay, I don't have the time to study it. Looks interesting, but I didn't study it. But where is it? It's disappeared because it was a branch which was irrelevant to society. Mm-hmm. So I think mathematics is useful when it is relevant. Otherwise, those are nice games.
Yeah, exactly. In mathematics, there is this sense that if it's internally consistent, you can come out with some kind of a model which will be very convincing and it will be logical. But just because something is logical, it is not true. And that's another part of the book I talk about. You can have logical statements, like you say, Saleem is a mammal. All mammals have 4 legs. Therefore, Saleem has 4 legs. Because it's a logical statement, but it's not a true statement because one of the premises is wrong. The premise being that all mammals have 4 legs. So this kind of dynamic happens with mathematical applications, which are not, which may have foundationally errant premises. And so I was just earlier on mentioning to you the work of Sabine Hassenfelder, who's a German physicist, and she wrote a wonderful book on this very topic. It's called Lost in Math, and it's about the misapplication of math in the world. She talks about economics and other fields as well, so absolutely. But it goes back to the human proclivity for pattern. Mathematics gives you pattern. So people are attracted to it. It gives a certain authenticity. It gives a certain sense of predictability even with probability you get, that's the part of mathematics which is least predictable, so to speak. But even there you get some sense of, percentages of this is the likelihood and so on. And that gives a certain comfort zone to people. And the other way in which mathematics then gets applied in social phenomena is how we perceive risk. But the irony is, risk perception, risk data, which is something that can be used in social decisions, that's where often you do not apply it because then human emotions take over. So you were giving the example of Fukushima. Fukushima, if you actually do a risk analysis, mathematically look at how many people died and so on, how many people died of radiation exposure in the Fukushima disaster? Anyone know? 0. Everyone died in the tsunami, right? There were about 14,000 people who died, but they died in the tsunami. If you look at the risk data in terms of 10 years after Fukushima, the International Atomic Energy Agency did a study of what was the cancer clusters, probabilities of that, people reporting incidents, and you can do detailed data analysis. Nothing found in terms of definitive cancer clusters. Some thyroid cancer changes were found, but they could not attribute them. And then you have mathematics of attribution, of whether you can say that, that's going to be there. But the decision that Germany made was based on emotions. It was not even based on the data. It wasn't even the risk analysis. And so you have this happening time and again then, where you don't have that decision making.
But you see, here is something very controversial. Because Fukushima happened in 2011. And even as yet, those reactors the radioactivity from them have not been contained, has not been contained. It will take another 40 years to do that. Something like $60 billion so far has been spent in trying to contain that radioactivity. The water is radioactive, so they're building tank after tank after tank, huge storage tanks. But they can't put it into the sea because then the fish will get contaminated. So it's complicated. It's one has to, of course, do a risk-benefit, cost-benefit analysis. But in this particular case, you will have many people who will be disagreeing with you.
Well, you know, the problem which I have, someone will ask me, are you pro-nuclear or are you anti-nuclear? I say, I'm not pro-anything. You know, it goes back to what Carl Sagan said, I want to know, not believe necessarily. It's just a matter of figuring out what does the data tell me in terms of the choices we have, right? So we have all these different choices, we'll have trade-offs. So if we want to not have nuclear power, then we need to have other forms of baseload power. I'm fine with that, okay, then you find other sources of baseload power. If you look at the risk analysis, okay, yes, there is you have to look at what the cost of the $60 billion is partly because the level of risk aversion with nuclear is far greater than with other sources of power. I'm a big proponent of wind power. In Delaware, we have a major wind power plant. But the reality is, if you're concerned about wildlife, you have more birds dying of the wind turbines than you have of, even if you have a leakage of a nuclear reactor every now and then of some kind, you do not have the same mortality, morbidity rates. So, you know, then you have to look at it that way. My biggest concern with nuclear, of course, would be in terms of the actual sustainability of the fuel. You know, how much uranium can we have to be able to supply? Can we have other kinds of breeder reactors which can provide that? If you look at it from the point of view of entropy, you know, with wastes, as someone who does environmental system science, I would say, what kind of waste should you have? Do you want a low entropy waste or a high entropy waste? Does everyone know what entropy is? Entropy is a measure of, again, simplifying in front of a physicist, but the level of disorder in the universe, right? Entropy. But so how would you want high entropy wastes or low entropy waste? Low entropy waste? Yes, so exactly. So what is nuclear waste? It's very low entropy waste, because it's all produced in one. If you burn fossil fuels, you have very high entropy waste, because you're just, you know, it's all going up, and you can't bring that, you know, carbon capture and storage, which we're trying to do, so difficult to get all that carbon dioxide back and try and sequester it, right? So from the point of view of then going again to the fundamental laws, having low entropy waste makes sense in that regard. Other kinds of low entropy waste you could get from, you know, well, you could have high entropy waste which is not of much consequence, like hydrogen. Hydrogen will produce, if you burn hydrogen, what do you get? Water, you know, water vapor. So it's high entropy water vapor, but who cares? That's fine, right?
You know, I don't want to take up your time on this issue because it is a little controversial.
Yeah.
And we'll move on. But I have to tell you that I'm one of the people who went to court against the construction of nuclear power plants in Karachi. Because if something happens over there, there is not a chance that Karachi can be saved, because the infrastructure does not support evacuation from there, as happened in Fukushima.
Yeah.
Remember that in Fukushima, the death rate was so small because it was such an organized society.
Agreed.
Let me also tell you one example of how organized they are as compared to us. In 2005, you remember that earthquake which hit this part of the country? That was an earthquake of magnitude 7.5 on the Richter scale. Just a little bit before that, some months before that, there had been an earthquake of Richter scale 8 point something, which means much more violent in Japan. In Japan, something like 70, 80 people died. Here, more than 100,000 people died. So there's a huge, huge
True.
difference in terms of organization. So if something like Fukushima happens in Karachi, that city is gone. My city,
I think
where I grew up, is gone.
You're absolutely right that that kind of decision though is made on then the risk profile of the governance system under which those kinds of facilities are operating. And there's another notion in terms of how can we make those systems around these kinds of high-risk phenomena, what we call anti-fragile. That's a term from this guy who has written a bestseller book, The Black Swan. You may have heard of Nicholas Nassim Taleb. He's a risk analyst at NYU, and he came up with this term anti-fragile, which means that you want a system which will actually get stronger with some disruption. So fragile systems are which will break with disruption, but anti-fragile systems are which will get stronger. And Japan is a very anti-fragile society. It actually learns from its disruptions and becomes more resilient. So because they have had all these tragedies upon tragedy. I mean, it's the most risk-exposed society. They have everything under the sun, from earthquakes to volcanoes to tsunamis to typhoons, every calamity on earth, and it's a highly dense population country. But they have developed this kind of anti-fragility around the way in which they operate. But if you don't have that, then obviously you make different decisions.
Okay, that makes a lot of sense. Now, we don't have a lot of time. So, towards the end of the book, you come to your conclusion, reconciling orders, lesson 1 to 5. Just tell us maybe one or two of the major lessons that you want to convey from your writing this book.
So, one of the fundamental lessons is that there is such a thing as irreversibility in terms of functional order. And functional is an important word and goes back to also what you were saying about fractals and the coastline. You don't need to have, for functionality, you don't need to have all of those measurements at the micro scale, right? So you decide, you make some rule about this is how we're going to measure the coastline, right? And that functionality is what matters. And that functionality may be dependent on what you want to do with that particular measurement. If you're doing the measurement just to develop some kind of a map which is going to be able to tell people around the world, this is the amount of acreage, real estate acreage we have on Britain's coast, right? That could be one functionality. Then you have a different scale. If you're going to be developing a map which is going to be looking at seaweed habitat in UK, you have to have a much lower functionality of that map because you want to be able to see where the little pools are, where the seaweeds could be or whatever. So that's one goal, is figure out in terms of what is the functional order that you want to present. And that's one lesson. And that functionality is going to be also then considered in terms of what is reversible and what is irreversible. So in chemistry, we have this notion.
So on this, you're saying don't look more carefully than you have to.
That's right, exactly. That's one key lesson. Then the second one, with building on that with reference to the irreversibility aspect. There are a lot of phenomena in nature which are functionally irreversible. What is one in terms of us sitting in this room, which we all know is functionally irreversible, but we don't advert to it, is death, right? Death is functionally irreversible, even though we cannot figure out a way to, even if you fix everything, after someone dies, we cannot bring that life back. Now, people then go into supernatural aspects around it, but there is a biochemical explanation for it as well, of why. And so that irreversibility of functional order is something that is really important for us to understand when we are concerned about also things like climate change, because we get tipping points, certain kinds of tipping points in natural systems where it is functionally impossible to bring it back, even though theoretically it may be. Aging is another interesting one related to the life and death phenomenon. And actually, MIT did a competition about 15 years ago that could anyone come up with a biochemical reason why we cannot reverse aging? Okay? Because aging is a biochemical phenomenon. It's an oxidation phenomenon, right? So our bodies are oxidizing. That's why we eat, antioxidants are so popular, because antioxidants are somehow reducing the oxidation of the biochemical aspects of our growth. And so and they did a competition, say, okay, come up with a reason. No one could come up with actually anyone. There was one guy who got an award for it because he came up with something close enough, but he still couldn't, and I mentioned that in the book.
But why take such a hard problem?
Yep.
Take a glass. I
Yep.
mean, this.
It's much more difficult.
I break it. It shatters.
Yeah.
It can't be put together again.
Well, it can be, but
There
it won't
is-
look exactly the same.
That.
Yeah.
I was mentioning the fact, like you were saying there was a competition and people were given the assignment to figure out if they can reverse aging in some way. But my point was, there are so many organisms which do not go through the process of aging or death.
Yeah.
So if you study those organisms, you should be able to figure out the reason. Whether you can, do something about that or not, that's a different thing.
Yeah.
But you should be able to figure out something from that.
No, so what the competition was about was that can you come up with a biochemical explanation for why aging could not be reversible? And no one could. So what basically the idea was that biochemically it could be reversible, but functionally it is not reversible. And so that's what I was trying to get at is, and the reason for that is because you get to certain levels of these kind of processes, these chemical reactions, which are going to be because you'll have to inject so much energy into them that they will functionally not be reversible, right? So that's the other part of it, is that how much energy are you willing to invest in something to be able to bring it back to that point. And with reference to the point about life and death, though, there's some other aspects which are there as well, because that has to do with emergence. There is this notion in complex systems theory around emergence, that when you get a certain emergence, that emergence is unidirectional. It cannot be brought back exactly to the same point as well. So there are two different sides to it. And this also has to do with the difference between complicated and complex. So you have, for example, a car or an aeroplane is complicated because it has many different parts, and each part has modularity, and you could replace it. But a complex system is not modular that way. It's emergent. And so that's the other difference aspect, and with complex systems, the amount of energy investment to bring it back exactly to the same is so large that it's functionally irreversible.
Probably I think it has more to do with the entropy. It's possible, but the probability of doing it is so low that it might not be possible. Like if you put the cream in the coffee, it would melt as per the principle of entropy. It can also do the other way around. It may not melt, it can solidify. But physically, the probability of that thing happening is like 0.0001, so less. That's why it does not happen. But it's not like it's not possible.
But that's
it's
why
only
I said
the
functional.
Probability is very low.
That's why I've used the word functional, that for functional purposes, and going back to the first point, that you don't want to analyze to the point where it's not of much use. So that's the other reason why.
Actually, I will answer your question, but after
Yes.
Dr. Saleem finishes. But that's a point that needs to be taken up.
Yeah,
So
and-
please continue.
Yes, so another key lesson to of the book is that order can be discovered and invented. I'm very careful that I'm not an environmental determinist, There is this notion of those, within, especially in my field in geography, which is geography has both a physical side and a human side, right? Physical geography is very much like natural science kind of fields. And there's this fear that in geography, the physical geographers tend to be very deterministic, and they will say that, oh, the environment will determine how societies behave. So you have a certain kind of people living in a forest, and they will behave in a certain way because they live in the forest. What I am saying in this book is not deterministic. I say that order can be discovered and invented. There is a certain order of the forest. There's a certain way in which the ecosystem functions. But human beings have a specific quality in which they are able to invent order also. That is why in geological time now there is a recognition that we are living in the Anthropocene. There are these periods in geology which we talk about, like the different we're living in the Holocene period in terms of geological time, but now there is consensus that we should define our current geological epoch as the Anthropocene, because we have the ability to change and invent order more than any other organism. And so that's the other key lesson, is that it's not deterministic. Human beings have the ability to, and that's where I tend to be more optimistic than many of the other environmental sort of popularizers of the environmental discourse these days, because I do feel that human beings have the ability to adapt in a way which is going to allow us to have a future which may not be the ideal future by many standards. It may be like science fiction movies like Blade Runner or Waterworld, or there are futures which are not ideal, but there is adaptive capacity which we have that will allow us to develop that. So that's another key lesson, is the order can be discovered and invented.
Coming to your last lesson, lesson number 4, tipping points can lead to accelerated order or disorder. Now, one tipping point I think is very worrisome, and that is what when the temperature becomes large enough for the stuff beneath the Arctic to start releasing methane gas. Once that starts to happen, then we will have crossed over to the point where there'll be more and more carbon dioxide, greater and greater temperature, more and more release of the, I don't know how many trillions of tons of methane down there, which means things will be out of control.
Yeah, absolutely.
How real is this fear?
Yeah, no, there is this notion of planetary boundaries. There's a Swedish environmental system scientist, Johan Rockström, and he's now the head of the Potsdam Climate Institute, and he came up with this concept called planetary boundaries, that there are these different key variables for human beings to have a sustainable existence that we need. Like the ozone hole is one example, the stratospheric ozone. If we do not have stratospheric ozone, I mean, that's a very clear one, because we would have ultraviolet radiation coming to us, which would lead to so much cellular abnormality, and that human beings would not be able to procreate and so on. So that's a very real one. Thankfully, that's one we were able to deal with. Surprisingly, that was one where we came to a consensus. We established phase out of chlorofluorocarbons, which were depleting the ozone layer. Similarly, you have these tipping points which can happen with some kinds of climate change, and methane release could be one of those. Clearly, we have also a history of knowing about how climate change tipping points have happened with reference to volcanic eruptions, when so much sulfur was put into the atmosphere, which led to a cooling tipping point. You can have the reverse tipping point with sulfur. So that is absolutely a fear. Now, one could say that now technologically we could adapt to it in certain ways by building infrastructure. There is a whole field of geoengineering which is around actually changing the atmospheric composition itself by having what they call solar radiation management. There are a lot of people who are working on a very large scale planetary adaptive strategies. So there are tipping points. It's what we call positive feedback loops, and often positive feedback loops end up being negative for society because they are causing this kind of domino effect. So yes, you're absolutely right that with climate change that could be a concern, but I tend to be one of those people who feels that adaptation is something we should now be focusing on because mitigation is very difficult to achieve currently, and we're seeing that now. Historically, 90% of donor funds have gone to, climate change funds have gone to mitigation. Only 10% have gone to adaptation. I think that has to change because the mitigation is just not playing out. We've had 20 years to do it and we're just not succeeding as much as we needed to.
So as we move towards earthly disorder, let's, anything else that you would like to add before we open?
I think we can have a discussion with the audience. So,
Since I have the microphone, that gives me the right to ask the first question. My question is like, it looks like the human brain has a positive bias towards putting things to order. We are fascinated by order. We like the order, the way we plan the cities, with the way we, plan our backyards and, within the homes. Like we put everything to order. And unlike other species, maybe other species also like the order, but to a lesser extent. But human mind is especially fascinated by, by this orderliness. But there's also a theory in psychology, like the personalities of Hitler, Mussolini, dictator like this, is an outcome of liking too much order in a human society. So how much liking an order is good and how much is
that's
bad?
That's actually one of the other lessons is also that that order should not be normatively good. In fact, order is what leads to prejudice, right? The sense of order in societies and so, stereotypes, when we have a stereotype about a community, it's because we are analyzing patterns beyond what is appropriate. There's a wonderful Nigerian writer, Chimamanda Adichie. I don't know if she's a MacArthur Fellow, amazing. She has a TED Talk, which you cannot watch, and it's called The Danger of a Single Story. And in that, she talks about stereotypes and this perception of order, and she says, the problem with stereotypes is not that they are wrong, but that they are incomplete. So there is always some kernel of truth in a stereotype. And it's that notion that our brain has of trying to find order, because that's how we're able to make sense of things. But that it's incomplete. And that's where nuance comes in. That's where I'm very cautious about how we think about order. So yes, point well taken.
And it is the exercise of intelligence, really, which then lets you explore outside of the given order.
Yes, absolutely.
Sir, thank you for a wonderful talk. If you were to write a second edition of the book, what would you change?
If I were to write, I would expand it. I wish I had more space to actually cover some of the topics. One of the things which I would have wanted to spend time on is adaptation and issues like geoengineering and those aspects of what are the ways in which human beings can engineer order, and what could be the limits of how we consider the role of engineering. And I wasn't able to do as much on engineering in the book. I talk about it in a few areas, but there could be a whole new enterprise around adaptive infrastructure. And recently, in my empirical research, I've been asked to look at, for example, deep sea mining. There's a huge controversy about whether we should be going into the deep sea and mining or not. And it's a situation where people are saying, well, you're trying to invade into this part of the earth which has been so pristine and no one has gone. We're talking about 10,000 feet below the sea, so in the deep sea. And then on the other hand, there's the solar radiation management. And so, there are calls for a moratorium on both, that we should not be engaging, that we're trying to play God, as they say. And so I have not had a chance to cover some of those aspects. That would be another one, maybe in the next book. So my next book, which is almost done now, is a very different take. It's a deep dive on one element, which has transformed our lives in ways which we didn't think. And you know what? Which element that is? It's an element which is the most abundant in the Earth's crust, but it does not exist freely.
Lithium?
No.
But I was going to ask you about lithium mining.
Lithium I can talk about, but no, it's not lithium. But lithium is an important one. But yes, silicon is not. It's not a metal. But yeah, but you're right. It's. I was talking about metal. Silicon is very abundant also, but it's not a metal. Aluminium, as you say. Aluminium is the. It's the most abundant metal in the Earth's crust, and it has. We did not even have metallic aluminium existing. People didn't even know it was a metal until about 150 years ago, because it is so tied up with oxygen that it's so difficult to extricate. And so there was a time when aluminium was more valuable than gold. But because we found out, this is where technology comes in and engineering, we found out a way to extract aluminium from bauxite. And it has become now so abundant that you drink your Pepsi in it. It's unreal. I mean, so it's a fascinating element. So this is the new book will be, and it's titled Soil to Foil.
Lithium batteries.
Lithium, I can talk about lithium. Lithium is a fascinating metal. It's an alkali metal. It's the lightest metal in the periodic table. And again, it has, it goes back to the point about what are some fundamental constraints which we have. Why is it that lithium is so important for battery storage? In all our cell phones, we have lithium-ion batteries, right? The Nobel Prize in Chemistry 2 years ago was given for the invention of the lithium-ion battery. Because lithium is so foundational to the way our lives have changed. Why can it do it? It's the lightest metal, very high energy density. It can store charge in that way. Now, people would say, what's the other far more abundant alkali metal which we could have potentially used, which is in the same group of the periodic table, which is the other metal like that, with lithium close to it. Just a little sodium, right? Sodium we have far more of. We have the Cura salt mines. It's in some ways similar chemically, but the problem with sodium, then the reason why lithium is better, going back to fundamental constraints of its electrochemical structure, is that it's much more flammable. If you try to make sodium-ion batteries, it's very difficult to be able to control them. And you don't want your cell phone catching fire all the time. So you have to figure out that balance. There's so much of natural systems, and I talk about this, it's this Goldilocks zone. You have to find not too hot, not too cold. A lot of what we do is constantly figuring out. जैसे कहते हैं आप उर्दू में कहें जी एक निज़ाम है, एक मीज़ान है, जिस तरह मीज़ान का जो concept है, which is certainly in our cultural and religious tradition is also brought up, that mizan, that balance, that Goldilocks spot, not too hot, not too cold, not too energy dense, not too, constantly comes up. And that's where we have to find those points. And even in the universe, we talk about the Earth is a Goldilocks zone. I mean, it's highly improbable that a planet with exactly these characteristics would allow for carbon-based life to evolve, because of that Goldilocks phenomenon. There's in fact a book by, I think, Paul Davies, one of the physicists, called the Goldilocks zone or Goldilocks planet or something like that. So, yes, please.
Thank you so much.
Talking about functionality of order.
वो तो पहले वो अच्छा आप कर रहे हैं उनको जी ओके आप कर लें कोई नहीं either way.
Sorry. You're talking about functionality of order. Have you studied functionality of chaos? And if yes, what are the examples and what was the outcome of that? Did that lead to an order, or it was just a waste, or it ended up nowhere?
No, you need, so for diversity of order, you need chaos. You would not have diversity of order without chaos. So that's why chaos plays a very important role, because it allows for the diversification of order in different forms. And that is what has allowed different species to evolve and so on and so forth. So at some fundamental level, that's the role of chaos, is the diversification of order.
So what you're saying is chaos is a transitionary phase of order, or?
Well, it's not necessarily transitional. It can be, depends on what kind of energy investment you make at that time. You could have a system which is staying in a chaotic state, but usually there will be a tendency for convergence in some form. So one example we have and I have a graph in the early part of the book, the relationship between entropy and complexity also. You can have, so like someone was giving the example of coffee and milk. That's the classic one, what Sean Carroll, a physicist at Caltech, he uses that example a lot, is that you can have, when you add milk to coffee, you will, initially you get a system which gets very complex, and you get higher entropy and higher complexity. But after a certain point, the entropy will keep going up, but it will become less complex because it becomes very homogeneous when the coffee and the milk are mixed, right? So you can have that kind of relationship also, where the entropy is still going up, but you're getting less complexity and you get homogeneity.
Yeah, I wanted this. I wanted this question to be answered because I'm a strong believer in predetermination, and I think that all events are predetermined, or events in individual life and events in the universe are predetermined. I've got lots of examples to cite, and that discussion is for another day. But I was wondering if you have seen this in this perspective. Your the topic of tonight. Have you seen that in that perspective? Because there are some real life examples. For example, evolution of human beings, how human beings evolved, and for a very long period of time, for millions of years, it seemed very chaotic. When the great apes, they descended from the trees, and they were living in rainforest, going from one tree to another. They had no reason to come down, but then the rainforest converted into savannas, and where the trees were scattered all over, and they had to come down, and then they became bipedal and all that.
Yeah.
So it's like it was predetermined and at that time it seemed very chaotic. So it was like predetermined that the human beings had to be evolved. I'm not a religious person, not at all. I'm not thinking that there's a bearded guy upstairs and who's guiding others. No, I'm saying.
Yeah, no, I understand what you're getting at, and there is this perspective, and I talk about the Gaia hypothesis. The Gaia hypothesis is that the planet itself behaves like an organism, that it creates an environment for which life is then developed in a way which is almost predetermined. But the Gaia hypothesis, you can take it metaphorically. The other thing I'm very careful about in the book is not to take, it's very tempting to take metaphor and then convert the metaphor into a sense of reality. And so there were people like Lynn Margulies, who was actually the wife of Carl Sagan, but then later on she was eclipsed by him for a long time, and then she blossomed as a scientist herself after they divorced, and she did an amazing job in terms of understanding the Gaia hypothesis from a scientific point of view. And so there are some aspects of that where you can have positive feedback loops which lead to conditions which may then later seem they were predetermined, but they're not necessarily predetermined, So I think you have to be very careful in then evaluating that. But the Gaia hypothesis is an example of what you're saying. And there's one chapter in the book which deals with that.
And there's a huge danger, as you say, of taking metaphor and saying that this is reality.
Yeah.
Look what's happening with Bharat Mata.
Yeah.
They actually think that all life originated there, that India was where it all began.
Yeah.
That comes when you take things too far.
Exactly.
No, that's not a credible theory, or whatever statement. What Indians are saying right now, that's stupid, that has nothing to do with reality. So.
Yes, but the point is that you take a metaphor too far, and that's what happens.
Yeah.
You have talked about the emergency legislation. I want to ask you that we all know that nuclear energy is one of the best source of energy to be used for constructive purpose. Why human tendency is towards its destructive use? Why humans are not having benefit from this energy, either than using it as a clean energy rather than dirty energy? Why is it?
मतलब nuclear power, any kind of जो आप कह रहे हैं ना कि any source of energy, it can be used in different ways. You can have, it doesn't have to be nuclear, hydropower also can be. But I have in the last section of the book, I talk about political order and how security can be connected to notions of order. And unfortunately, what happens is the way in which our political order has developed is that because of distrust between human societies, any kind of source of energy then becomes a source of security power. And it doesn't have to be just nuclear. Dams ka dekh lein, hydropower ka bhi yahi hai. And so in the third part of the book, in political order, I talk about why we have had this problem of decoupling of political order with understanding the constraints of natural order. So we try to then co-opt any energy and use it for security purposes. That's what happened with nuclear energy. It became used for nuclear power. But it has happened with all different forms of energy being used for whatever it is. It's just because nuclear has other certain characteristics which can be weaponized, and so it becomes much more so. So anything, but we have a tendency to weaponize other things too, and that's another fundamental challenge which we have in terms of the creation of nation states. Nation states are a form of creating order, right? We create nation states based on our, and I have a chapter in there where I talk about borders and order. And borders and order, when political borders create securitization dilemmas, which is where you get nuclear arms races, and you have these kinds of phenomena. And the fundamental aspect of that is it goes to game theory and an erosion of trust. When you have an erosion of trust, you create orders which are destructive in human societies. And that keeps feeding on itself then. So, if you look at the Star Trek universe, and I'm a big Trekkie, and I think it's a great, Gene Roddenberry's vision of Star Trek was to try and give people an understanding of the future, which is very much predicated in some of these notions. So, for example, one of the things in the Star Trek universe is that there are no countries, right? There are two things in the Star Trek, no countries and no one other thing. Any other Trekkie person here? No money. There's no money in the Star Trek universe and no countries. And the reason, the mythology in the Star Trek universe, why there are no countries is because after first contact, if you see the Star Trek 4, the movie, you'll see, after first contact, which is when humans first encounter another species, they suddenly realize that we should not have order on countries because we have this other external potential foe, and they all unify and they create United Federation. And so that's another dynamic and what I hope is that issues of environmental sustainability would get people to think the same way, just like thinking of some external entity which would prevent it.
So one way of looking at civilization is that the day we learn to make tools, we rose above the nature. So maybe we have given rise to some things new, like economics doesn't exist in nature, right? So we kind of went at war with nature. So how would you see, we are looking at nature to find solutions to the problem that exist in our society, which is not part of nature. Mm-hmm. So don't you see this is like paradoxical if we look at natural order, natural systems to find solutions in our problems? Maybe we are like looking at the wrong way of.
Well, first you have to ask yourself why we went against nature. And the reason for that is because in the early days of human civilization, we had abundance. When you have abundance, you do not perceive scarcity, which leads to that kind of behavior, right? And so that's why it was not on the horizon. The economists, the neoclassical economists, they frame the environment as an externality. If you read even now microeconomics textbooks, they have a whole section, externalities, and externalities, environment is one of them. Because the market cannot capture it directly, right? And so that's why that happened. Now when we have so much scarcity, I think, of resources, and we are dealing with these planetary boundaries, we have to think about it in those constraints. Because otherwise we are going to end up with an alternative future which is suboptimal in so many ways. It would be suboptimal both in terms of our own sustainability, but also in terms of the number of species on the planet and so on and so forth. And then there is, extinction is also something that is a natural phenomenon. I mean, we've had many extinctions. We've had 5 major extinctions naturally, Some of them were caused by geological factors. One was caused by an asteroid hitting the planet, the dinosaur extinction. And it's quite possible that, we could have extinction in our future too. But I think we have, because of that specific quality, the adaptive quality, I think there's a lesser chance of humans going extinct because of that. I think there's the most chance we have of going extinct is not because of our own activities. I think we can adapt to that. It's probably the asteroid phenomenon. Asteroid phenomenon could make it massive, or a supervolcano.
This is my point. Like, a species which goes extinct doesn't fight nature. They just accept nature. They flow with the nature. We started war with the nature by starting civilization, by giving rise to new
systems. And it's given us the ability to adapt more.
So I'm saying that this sustainable development concepts, all these concepts, that we have to go back to the past. I think, will it work?
No, I don't think we should go back to the past in terms of, that's not what I'm arguing. I'm not saying that we should go into a kind of, and there are people, I might say, there are environmentalists who feel that we should go back to a kind of a subsistence lifestyle. I do not think that is tenable. We need to work within the current technological system. In fact, I use the term, we are now living in an industrial ecosystem. Industry is part of our planetary system. And so we have to think about how industry can function more in cyclical processes. And that's where the next book on aluminum, and I keep saying the American pronunciation, aluminium will be important, because aluminium gives us a way in which we can think about a circular economy within an industrial system and how we can do it, because aluminium is highly recyclable. Once it has been extracted, you can find ways of using it much more in a cyclical way than other metals, because it doesn't oxidize that well. Well, there's a very thin layer of oxidation which basically prevents any further erosion, so you can use it much more.
This question is actually a direct continuation of the previous one. I would like you to elaborate a little more on adaptive strategies and what are the scholars proposing in this regard. One very obvious means is finding clean energy technologies, but as regards the way we live, our consumption patterns, etc., what is being proposed? How can we adapt or change those to sort of avert an environmental disaster?
Yes, so this is a real debate overall in sustainability is population versus consumption. And there is a chapter in the book about population, and this is a very contentious topic because often people in the developing world, such as in Pakistan, which still has such a high population growth rate, they say, well, why do you blame us for population? Blame the rich countries for consumption, because per capita consumption is much higher there for resources. I think we have to do both. I don't think we can just shift the burden on consumption. I think population is part of, there's a very famous equation that, it's a heuristic equation, not one you calculate, but it's the IPAT equation. Impact equals population times affluence times technology. Paul Ehrlich, the Stanford biologist, used it like in the 60s, and it's a very effective tool. So I think all 3 variables are important. Population, affluence is consumption, and technology can be good and bad. Technology can exacerbate impact. Technology can have as a mitigating factor to adapt. So I would say consumption, we need to definitely reduce consumption, or we have to find cyclical ways of consumption, going back to the circular economy approach. But there is such a thing, what we call the rebound effect, and we have to be careful of that. And it goes back to this notion that efficiency is not necessarily a solution to our problems. There's a sense which engineers often have, is that efficiency, if you make systems more efficient, you will solve the problem. If you do not keep your eye on consumption, aggregate consumption, efficiency can be a problem because you get a rebound effect. So for example, with hybrid cars is a classic example. If you have a hybrid car, it's much more efficient, fuel efficient. What is going to be the actual consumption impact of a hybrid car? it depends on the consumer. For some people, it would have a rebound effect because they think that it's more fuel efficient. If they have the ability to pay, they will drive more. So the aggregate consumption will go up, right? So I think that rebound effect is absolutely key in keeping track of consumption. And efficiency itself should not be enough. So don't let the engineers just focus on efficiency. Ask them to then calculate the full consumption, but you can't shy away from population. I'm very worried about Pakistan's population situation. We can say that, population, there's this notion of a demographic dividend. Population can be an asset if you have the ability to harness the population's labor and activities for development, growth, and so on. However, population becomes a liability if you can't. So it's a very fine line between being an asset and a liability. And that's the challenge. Countries like Pakistan, Nigeria, I worry about a lot, actually. I've spent a lot of time in Nigeria. I worry about it even more than Pakistan because of the growth rate is much higher, the land mass is much less, and they have not utilized their enormous natural resource potential effectively. But I think consumption itself is not enough to look at it.
I think there's no fine line here. Population is Pakistan's number one problem.
Yeah,
Look at the way that land is being gobbled up.
Yeah.
If you had come here 10 years ago, you would have seen Islamabad half the size.
Yeah.
And now it is out of control.
Yeah, exactly. And if we don't use, we have not been able to harness the demographic dividend. And I don't think we can at this rate because our educational profile is so low. So we have to figure out other ways. The other ways would be to, but there's other migration is one other way, but that's not, if people were allowed to migrate, but that's where the other kind of political borders and order come in, right? Ideally, if you had a planetary view and you had free migration opportunity and you didn't have prejudice, then population growth at an aggregate level for the planet is not a problem. You have half of the planet which is undernourished and half of the planet which is overnourished. It defies belief. You have a multi-billion-dollar industry for people just to burn weight. They are going and treadmills and blah, 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 blah. These are people who are eating too much so they can actually burn the calories, and then you have people who are dying of hunger. So it's a distribution problem, but we don't have a functional order to do the distribution. So the problem is, yes, in places like Italy, population is going down. But do you think they will let brown people like us help them? No. So then what do? There's a problem with the political functionality of order not being in congruence with the other order. So then we have to look after ourselves. We can't just say, oh, gee, Italy wale bade bure hain. हमें अपना तो फिर भी करना पड़ेगा ना. अगर नहीं कोई और हमें जाने दे रहा तो उसके मतलब बेड़ा गर्क अपना करें.
One last question.
Yes.
So it says how natural laws define human life. Pardon my stupid question if I reverse the order. So how human laws define nature? Can you just share some thoughts on that?
Thank you. That's a really important point. And that goes back to the invention of order that I mentioned, that we have now the ability to redefine natural systems themselves. And that goes, but we will still be constrained by some fundamental foundational principles, and those go back to the physics and the chemistry and the biology side of it. But in other forms, yes, we are now transforming the landscape. There was one analysis done of the total biomass on the planet. This was a group in Israel who did this analysis of all of the total biomass on the planet. And what they found is now that human cultivated biomass is greater than natural biomass. So that means cattle, because we have started, the amount of animals which we now have for human consumption, their biomass is more than the natural biomass. So that in itself is scary.
And in fact, evolution of the species has been taken over by humans now.
Yeah.
It is we who will guide what direction evolution is now to take. It's now in our hands. Homo Deus, yes.
Yes,
Man is
Harari.
God. Man is God.
Yeah, yeah.
Yes.
Though he goes a bit off on a tangent with artificial intelligence, and he's become a bit deterministic that now humanity will cease to exist because the artificial intelligence, like Elon Musk type of approach. I don't tend to feel that we're going to go that path down there. I think there are too many filters to prevent that, where artificial intelligence will just make humans extinct, which is what Elon Musk says, that is
But the
biggest-
principle of natural selection
Yes.
is broken down.
Yes, no doubt, no
yes.
doubt.
Thank you very much, everyone, for being here. And thank you particularly, Saleem.